join. So no problem, we can start. I have already informed about the lecture now. Let me share the lecture notes. We are actually in the latter part of the chapter 5, right? We have already discussed a lot of theories, and now today we are supposed to discuss the waves in an air column. Waves in an air column. Okay. So last lectures we discuss about the standing waves in a string. String means actually it's like a rope, right? So now today we are going to discuss the standing waves in an air columns. You already know that what is standing wave, right? Air columns means now like your resonance tube practical. If you have a particular tube, right, we can close one end and we can open one end, so that inside that tube the air will be there if you are not putting any liquid or whatever. So then within that air column there will be waves, generated waves. So at the particular position the standing wave can be formed, right? So standing wave can be set up in air columns as the result of interference between longitudinal sound waves traveling in opposite direction. That means you know that you are using the frequency, no? You using the frequency forks to different frequencies. Maybe 50, 200, 200, 300 like that. You are using forks, right? Frequency forks to give the sound. So when you are giving the resonant sound you can hear. So that means what we are doing actually, we are giving the vibration to this air column using the frequency. That is actually the sound wave, right? So the phase relationship between the incident and reflected waves depends upon whether the end of the pipe is open or closed, right? No, now normally when you are doing the practical, you are keeping the one side of the tube open, right? So what are the features of this? Again, the standing wave notes are, notes means zero amplitude, antinodes means maximum amplitude. That is similar, right? That's standing wave features now. And standing waves can be classified here into three categories, right? Earlier, if you can remember, only two categories. Standing waves in a string. When we were discussing the standing waves in a string, we had two classifications, but now standing waves in an air column, we have three classifications. First one is both ends are open. Second one, both ends are closed. Third one end closed and one end open, right? So in these three positions, three classifications, you might see the standing waves in an air column, right? So we will see the further details. First of all, you note down, write the subheading as the standing waves in an air column. Then you can note these things as like point forms. First one, the first point, you can write the introduction for the standing waves in an air column, which is in the purple color. Then you can note down these features and the classifications. Please write it down. So according to the length of the pipe, earlier according to the length of the rope, no? Everything happened. Now according to the length of the pipe, how many loops can be generated will be varied. Right? We will see one by one the incidents. First of all, you note down this. Finished writing? Still writing or finished writing? Students?
Still writing, ma'am. Not finished.
Okay. And another thing I wanted to verify from you all students, have you all submitted your what we call this practical reports after finish all the practicals? Did all of you submit? Huh? Anyone didn't submit the reports? You all have to submit all the reports before the study leave, right? After the study leave, any reports will be not taken. And also, if you are absent for the practical, you can't submit the report. If you are absent, you have to give a medical report. And then, if you are given the permission, if the demonstrator is free, you can do the practical, then submit the report. Okay? All the reports should be submit before the study leave. That is compulsory. Finish writing. Shall I move to the next slide?
Yes, ma'am.
Okay,
Yes, ma'am.
now you can see here we discuss there are three classifications. So we will see one by one, right? First one is both ends are open. So you can see here this end, both ends are open. Open ends means what? There cannot be any nodes, right? There cannot be any nodes. It should be open. No, it's open, right? So the loop is not continuing after that, right? Loop is not continuing after. So then here you can see your loop is like this. So this is a half loop and this is another half loop, no? Then there are full one loop. Am I correct?
Yes, ma'am.
So this is the first, second node, third node, right? And fourth. So the wavelength, you know that here, let me write it here. If it is like this is we are calling as full wavelength, no? Lambda. Okay. So lambda means actually two loops if you're counting as loops. But here how many lambdas? Only one lambda, right? Because this is lambda over 2, this is lambda over 2. Am I correct? Eight to eight. This is lambda over 4 and this is lambda over 4, no? Huh, students?
Yes, ma'am.
Because you know that this full one is lambda. Full one is lambda. Then one loop means lambda over 2. This is lambda over 2. Here, half from the lambda over 2 is there. That is a lambda over 4, lambda over 4. So this lambda over 4 is fully equals to what?
Lambda over 2.
Yeah, lambda over 2. So lambda over 2 is equals to L, no? Because the length of this tube is L. You can see. So then wavelength is 2L. That is how this 2L has come. Right? And frequency is equals to, we know that equation, the very famous and the most important equation in the waves, V is equal F lambda. Therefore, F is equal V over lambda. Now we found the lambda is 2L in this incident, then V over 2L. That is how this has come. Right? So this way, we can count all these modes. And for example, if I am just telling this is lambda over 2, this one lambda over 4, this is again lambda over 4, right? So you can add all these together, lambda over 4 plus lambda over 2 plus lambda over 4 will give you the final result. Then that is actually here fully 4 lambda. I think full one is lambda, right? Then L is equals to lambda in the second incident. Okay. So like this, you can find lambda for all. And then if you know the lambda from V is equal F lambda, you can find the frequency as well. So here the whole number of the half wavelength is equal to the length of the rope or string. So we can modify this equation. Modify this equation for both ends are open incident in a tube. Okay. Yes. If you have any doubts or anywhere like problem, you can ask if you didn't understand anything in this part. Only thing you have to identify what is the wavelength here, right? Then that wavelength can be equal to the L because the total this what we call wave is inside the tube, no? Right? You have done this practical, no? What you are doing normally here like this one cylinder you are taking and then you are filling the water to this one, then putting one tube inside. And taking a cylinder like this, measuring cylinder or something. Then after that, you are putting one tube, no, inside. You have done this practical, no?
Yes, ma'am.
Then you are filling the water, right? So you are using a stand or something to hold this one. Then here you are keeping the fork, right? So then you are changing this, what we called the height of the tube, right? When you are changing, the air column will be changed. Length of the air column. So length of the air column only this L, right? So in that L only like this, loops will be formed inside, right? So when these loops are, when this frequency, this frequency is equal with the frequency of your fork, only you are hearing that resonance sound, right? So you can see when the L is changing, the frequency of the particular wave is changing. No, here V over 2L, here V over L, here 3V over L, 2L, right? So different times. That's why different resonance frequencies are there. Understood the practical? So this one only you have done in the laboratory as the resonance tube practical. Please note down the needed things. Draw these pictures very carefully. If you think like my writings are unclear for your writing, then just let me know. I'll clear the board. Right? I didn't clear the board because I thought if you need anything from my discussion, that's why I kept it. If you feel like it's uncomfortable, I'll clear the board. Just finish it off and tell me. Yeah? Still writing, students? Anyone is writing still? No. Okay, then we can move for the next one. The incident when both ends are close. So you know that when both ends are close, there can be what we call nodes, no? There can be nodes. So the full loops you can see. If the both ends are close, you can see full loops. It's like both ends clamped string, right? String or rope. If you are clamping both ends like this only in a string also, the waves will be generated. Now, if you are closing the tube like this, we can see what we call the nodes in both sides. So then full loops will be there. So now here you can see obviously this first one, uh, L is equals to lambda over 2, right? Then lambda is 2L. Then frequency is like this because V is equal F lambda. In the second one, you can see it's a full lambda, no? Because this is we are normally calling as the full cycle, then it's lambda. Lambda is equals to L. Okay. Here you can see this is here 1 lambda and here lambda over 2. Then altogether it is 3 lambda over 2. Therefore, 3 lambda over 2 is equals to L. Lambda is equal to L over 3. Right? So like this, first, second, third, fourth modes are generating and accordingly the frequencies also will be there. If you have any doubt, you can check these frequencies. Always apply the V is equal F lambda, then you can find this equation. Right? And here the common equation is L is equal N lambda over 2. When N is equal 1, right? N is equal 2. N means number of loops, huh? N is equal 3, you might get the L from this equation. Okay, please note down this theory of similar, same way, but different cases. Both ends are open, both ends are closed, one end is open, one end is closed. So different cases, that's it. Otherwise, there's no any new things. Similar things only always circulating with different cases. Any problem, please ask me. Don't keep any doubts. Huh? We will do some exam questions after we finish the theories. So first of all, you try to grab the theory. Please write down. And if the meeting is finishing again, please join with the same link. Students, finish writing? Shall I move for the next classification? Anyone still writing? No.
Yes, ma'am.
Then I'll still writing. Okay. Write it down. Finish writing.
Yes, ma'am.
Okay. So here, next case is one end close and the other end open. So the close end, obviously, you should have an antinode, and open end, sorry, close end should have a node and open end should have antinode, right? So then here you can see throughout the L, in the first case, there's only L over 4, sorry, lambda over 4, no? Lambda over 4. The wavelength, here it is lambda over 4. This one. Then this lambda over 4 is equals to L. Therefore, lambda is equal 4L. V is equal F lambda. F is equal V over lambda now again. So then V over 4L. So it is here. V over 4L. Right? So in the second case, what's happening? In the second case, there will be a full loop, one loop. So that is lambda over 2. And here another half will be there, that is lambda over 4. Altogether, this is 3 lambda over 4. Then when you are equating that one to L, you might get lambda is equal 4L over 3. Okay. Here you can see this is fully 1 lambda, no? Complete cycle. And another half, not half, quarter is there. So half loop, then quarter of lambda. So therefore, this common equation we can develop for this one is L is equal n lambda over 4. Suppose n is equal 1, then what will happen? L is equal lambda over 4. Lambda is equal 4L. This is that one, no? Right. So always you can use the common equation to find the lambdas according to the mode. First mode, second mode, third mode, fourth mode. So you can apply n is equal 1, n is equal 2. Likewise, you can apply and get the lambda, find the lambda. So you can note down the third case, one end closed and one end open. Draw all the modes, first, second, third, and fourth, and the wavelengths and relevant frequency values. Finally, the common equation. So you might see all these cases are actually similar. The things we are discussing is similar, but different applications. That's why you might see the final equations are a little bit different from each other. If you can't understand anything, please ask me. Have you finished writing?
Yes, ma'am.
Right. So we have discussed all the things needed for the waves and sound chapter, right? So what you can do is you can go through the lecture notes and you can get familiar with the theory. I will definitely do some related questions, right? Uh, when the exams are near, I'll do some questions. Now you can start the questions doing by yourself. You can find some past papers and you can start that. Next, we are actually going to discuss about the electric circuits. Electric circuits. Because I thought to finish this part and go to the next chapter because this is normally every time the questions are coming, very basic questions. Electrical circuits. So I will share it. This is actually the last chapter, but we have some other small parts to discuss. Electrical circuits. So these are the learning outcomes that we are going to discuss within this chapter. What are the principles related to the electricity? Right? You have done the Ohm's law practical in the practical session. So we are going to discuss the Ohm's law, Kirchhoff's law, right? Definitions and what are the equations and how to do the electrical calculations using this Ohm's law and all, right? And what are the basic types of electrical circuits? These are the learning outcomes of this chapter. Normally, the electrical circuits or the current is flowing according to the electron move, right? Maybe in your chemistry, you are learning about the electrons, protons, and neutrons. So you know that basically the neutrons and protons are inside the nucleus and they are not actually giving any contribution for current, but the electrons are moving around the nucleus in their own orbits. So the electrons will contribute for the current, right? Generation of the current. So electron theory. So we will just basically discuss about this, but you know all these things we are discussing deeply in the chemistry. Atoms are the tiny particles that matters made up, right? So atom having three things: electrons, protons, and neutrons. So basically, you know the electrons are negatively charged particles, protons are positively charged particles, and neutrons are neutral particles. They don't have any charge, right? Zero charge. They don't have any charge, so they are neutral particles. So that here, normally, these neutrons are and protons are including in the nucleus. We are calling it as nucleus, right? Inside the nucleus, only neutrons and protons are there. Around the nucleus, it has orbits, right? So in these orbits only, electrons are moving. This is what the Rutherford experiment, and there are a lot of things not maybe you are learning in the chemistry. So that's not needed here. Uh, the scientists found how the electrons are moving around the nucleus, right? So this is one of the picture for that. You can see this is the nucleus inside. The nucleus is positively charged because protons are inside. Neutrons are not giving any charge. That's why nuclear, they mentioned here positive sign. Positively charged, and these electrons are negatively charged. You can see electrons like this small line is there. That is indicating it's negatively charged, right? So these are the orbits around the nucleus. Normally, electrons are moving around nucleus in their orbits. Electricity is the flow of electron. This is important. What do you call by electricity? Flow of electron. Otherwise, electrons moving, right? Movement of electron, flow of electron from atom to atom in a conductor. So if we are having a conductor means what? So there are three things now: conductor, semiconductor, and insulator. Insulator means it's like rubber, plastic, right? Where the matter, where the current is not passing. Those are insulators. Conductors means the matter which our current is passing. Semiconductors have the properties of insulator and conductor both. It is in the middle range, right? So here the word conductor is there. That's why I mentioned that. Electricity is the flow of electron from atom to atom in a conductor. So if you are considering a conductor, maybe it can be aluminium, right? All the metals are conductors, no? All the metals are conductors. So in a conductor, atom to atom, the conductor is a matter and it has made up with the atoms. So each atom has electrons. Those electrons will pass from atom to atom. When the electrons are passing, we are telling that electricity is generating, right? That is what happened in electron theory. Please note down all this the basic introduction for the electron theory. Draw the picture as well, mark the nucleus and the electrons which are going around the nucleus. Anything? Each slide I'm asking you, if you have any doubt, please ask me. I'm giving more time for writing. That's why it's taking some time to finish the lecture, but I'll finish it quickly after 5 slides or something from this chapter. Because we are lagging, no? We have to finish it quickly to go to the questions. Please quickly write down, and after finish writing without being shut up, just tell me. Right? Okay. Anyone writing?
No, ma'am.
Okay. Right. So in this slide, we will briefly talk about the insulators, conductors, and semiconductors. As I told you, matter. Matter means whatever the things surround us, we can divide into three main categories. Right? Conductor, semiconductor, insulator. What is conductor? What is semiconductor? What is insulator? You should know. Right? Electrons are in orbits at different distance from the nucleus. That means now if your nucleus is like this, electrons are at different orbits, right? So different distances, no? This electron is this much distance for the nucleus. This distance, this new electron is this much distance for the nucleus. So what will happen actually? When the electrons are going far from the nucleus, far from the, because the other electrons like this were going far away from the nucleus, no? Far away electrons are less bound with or less bind with nucleus. Why? What is the reason? Because suppose your nucleus is like this. So nucleus has protons and neutrons and it is positively charged, no? Positively charged, right? So I will put it as positive mark. Nucleus is positive. So one electron is there like this. Another electron is there in this orbit. Another electron is there in this orbit, right? So this is electron 1, 2, 3. I'm just telling example. Electron 3, very easily we can remove. The reason is the force in between the nucleus and the electron 3 is very less because distance is high now. And electron 2 and the nucleus, it has another force. So maybe that force is little bit higher than the earlier force. So if this force is like this force is like this, and this force which is electron 1 and nucleus, it's very high. That is why we can't remove the first electron. We can't remove the first electron very easily. We can remove the third electron very easily because it's less bound with the nucleus. It is similar like when you all were in the school time, you people are there in the house now with your parents. So it's very difficult to break the relationship between the house and yourself. But now you all are very far away from the house, right? Sometimes you are feeling very free, no? Very free. If anyone needs to break your relationship with your house also, it's easily can be done because you are far away from your family, right? So the force between the attraction force between the what we call the very outermost electron and the nucleus is very less. No attraction force. So easily we can remove. That is what the second sentence says. Electrons in the orbit, the greatest distance from the nucleus are in the valence shell. Valence shell means very easily we can remove. So with these kind of shells we are calling as valence shell. And you can write down here, those electrons are, I will write it, those electrons are very easy to remove. In the bracket you can write. And the third point, the outer orbit contains between 1 and 8 electrons. Yes, that you know in chemistry. So what is insulator, conductor and semiconductor? Normally in the insulators, it contains, so it includes 4 electrons in the outer orbit, and conductors it's less than 4, semiconductors exactly 4, right? So conductors can conduct the electricity very easily. Insulators are not conducting the electricity. Semiconductors are in the middle stage. They are conducting and not conducting. Both can be happen. Right. Please note down all these points, and if you need, you can draw this diagram also. Please, this what we call all the orbit should be circles. So I can't draw it nicely on the whiteboard here. That's why it's like this. But all the things should be like circles. Please note down it. Yeah. So we will write about the okay. So here this is a little bit about the insulators and then conductors. Right. Insulators, some electro elements have atoms with valence shell electrons have the strongest magnetic attraction with positive charge in the nucleus. The meaning is valence shell means the outermost electron, outermost orbit. Right? I told that nucleus is there, then there are some orbits like that. No, which one is the very outermost? Outer. That shell or that orbit we are calling as valence shell. So electrons which are in that shell we are calling as valence electron. Normally in the insulators, valence shell electrons have more attraction with the nucleus. What will happen if it has more attraction? We can't remove that electrons. We can't remove the electrons easily means there's no any electricity, because if you are moving the electron, if the electrons are moving only, electricity will be generated, right? So that is why insulators are not conducting the current. So what are the examples for insulators? Glass, paraffin, rubber, right? Wood, plastics, those are porcelains, those are examples for insulators. So you should know some, maybe 3 examples for insulators, right? And you should know how to explain what is insulator and some examples for insulators. And these elements are poor conductors. Poor conductors means is not conducting the current, right? So this is about the insulators. I will send you this. I'll send you this, and the next one, it's about the conductors. Conductors in the sense, those are conducting the electricity very easily, right? So you can see that the examples. Most of the metals are conductors. Silver, gold, copper, aluminium, right? Those are examples for conductors. These materials are good electrical conductors. Some elements have valence shell electrons that have weak magnetic attraction. That means I told you, no, if the force between the nucleus and the outermost electrons are weak, then very easily we can remove those electrons. Easily removing means the electrons are very free to move here and there. That means current is passing. Okay. So this is basic about the conductors and insulators. So the next one we can do in the next lecture. I will send you that 2 slides. I'll send you the photos for your WhatsApp group so you can note down. So because I need to finish this now, we will start from the next slide in the next lecture. So in this chapter, we have some calculations using the circuit diagrams. Okay, so I'll do it in the next lecture, and please send your registration numbers to the chat now. These 2 notes about the insulators and conductors, I'll send you. You can look at the photo and you can write it down. Anything to be asked about today's lecture? You might ask any clarifications or doubts if you have. Please send your registration numbers. Please send your registration numbers to the chat now. And you can send the registration number and you can leave. if you don't have any question. If you have any question,
Excuse me, ma'am.
please ask.
Excuse me, ma'am.
Anyone has question?
Excuse me, ma'am.
Yes.
Ma'am, for the last lectures, I attended that lectures, but I didn't send the BST number.
Okay, no problem. I
Uh,
can find it from my chat in the attendance. I will do it. I'm
okay,
just
ma'am.
for clarification only, I'm asking you to send registration numbers. I can find it. No problem.
Okay, ma'am.